quarantine day. Looking from the response today, it looks like some people did it because now we don't seem to have many people listening. I mean, the number is adding slowly, but I'm sure by in the next 10 or 20 minutes, we'll have more people coming in. I would like to start by thanking you all for the persistence. I know this is a long and hard training, but we're happy that we still see up to now still 200 people coming in. I hope by the end of the day, we'll still go back to the number that we had previously. I also want to remind you of our main funder, which is the Makere University Regional Center for Copy Improvement. So if you are still planning to study and you're interested in studying MSc or PhD in plant breeding, I think Makere University would be the place for you. Our courses are good quality and is affordable in terms of tuition. Once in a while, we also have some scholarships here and there. So I will encourage you to check on the website of Mercy and of Makere University. So also, this is one of the centers of excellence that are funded by the World Bank. There are a number of them. I think we have one in for crop improvement, we have 3. We have one in West Africa and one in South Africa. So this one is for Eastern Africa. Yesterday, we also gave you people some assignment, and the day before. So I would like a few people to raise their hand up, then we can pick. And then if you're ready to present, then we can allow you to present. Before I start with what we left yesterday. Say, does Makere offer statistics at graduate level? Yes. But the statistic is more, we have at either the medical school, and then we also have at the department at the School of Statistics. So you can get more details from the website, the university website. Anybody ready to make a presentation? So Bedasa, can you give us a presentation? And then we have Lema. So we have those 2 to make a presentation. So the day for day 7 link will be sent later. But if you're entering and you requested some information when you're joining, then you should be registered. But we are going to get you a link for day 7 to register. So the link is for the material is going to come very soon, and we are going to give you a few minutes to download. So the Google link is going to be posted on the chat. So please stop posting anything on the chat so that we wait for Ellen to post for us the link, and then we give you, as usual, 10 minutes to download the link. While I request to have the 2 people to give us some presentation.
Thomas, kindly repeat the names clearly. I am not seeing them in the list.
Hey, I saw Bedasa said yes, and then Lema.
I promoted the Birhan, but I think it was not clear.
No, that's okay. That's okay. If you promoted him, that's fine.
And then there is also someone without a name called Techno.
Yeah, just any 2 will be fine.
Okay.
Yeah, thank you. Just
Most of them
get
are
us.
already okay. They should
Oh,
get set and start immediately.
okay, thank you.
So take notes. Please go ahead and do the presentation.
Well, whoever is ready can start.
Whoever is using notes, please go ahead because you have the right. I've promoted you.
Someone is saying, please be louder. I don't know, maybe they are not hearing. Maybe you could repeat.
There is also Emeka, Ustin Emeka. Kindly unmute yourself.
I think that one is not there.
Okay. So maybe you can put them back, Jolene. You can change them back to attendees. Yeah.
And anybody who is
I don't know, Dr. Odong.
yes.
People are saying sound, please. So I don't know whether what you had asked people had understood. Maybe you could repeat so that we can get more people trying to share their.
Yeah. Okay, thank you very much. Yeah, we gave assignment yesterday. I think Susan gave an assignment, and I also requested for some work to be done. So we are saying whoever is ready to make a presentation, let the panelists know, and then you are selected so that you give us a brief presentation.
Okay, thank you. I think Austin now is unmuted. I don't know whether he can hear us.
I'm hearing.
Oh,
Okay.
please go ahead.
Yeah. Good morning. I'm Austin. This is my first time of participating in the program, so I don't really have any presentation to make.
Sorry, I didn't hear you.
My name is Austin. This is my first time of joining. I just got the link. I had to join today.
Ah, okay. So you're not going to present. So, okay, that's fine. Maybe we can have someone who is willing to present. Let us know so that we can upgrade you.
Okay.
All right.
So the link has been shared. So please download material for day 7. We are going to start with material for day 6, the script that we shared yesterday. That's what I'm going to start with. So please make sure you download the link that has been shared, and please let's stop posting so that people can pick the link and then they download, then we can start. So as we wait for whoever is going to make a presentation, I'm going to start off. So I still want to repeat the issue of the funding. So this training has been made possible by Makerere University Regional Center of Crop Improvement in collaboration with the Aru Forum and Badea. So we also want to advertise a little bit what we call MASID as Makerere University Regional Center for Crop Improvement. We offer MSc in plant breeding and seed systems. We have a PhD in plant breeding and biotechnologies, and then we also offer short courses. This is one of the courses. So the main funder of this program is the Makerere University Center for Regional Improvement. This center is funded by the World Bank, and all the courses that are offered by the World Bank, they always have a feedback because they want to know whether there is need for additional training. So we expect that when they contact you either through telephone or through the emails, you should be able to respond to them. If you don't respond to them, then you will not have opportunity for future training. So this is our polite request. And we are also looking at, we are trying to come up with a certificate, but then you need to attend for at least minimum 4 days before you can actually qualify for a week in total before you can qualify for the certificate. So I would expect you to please be consistent and not just for the certificate, but we hope that you're learning in the process. So Bruno said raise the hand up. Okay, so if that is not, if we are not having people willing to share now, so we can you put Bruno on and see whether he can say something? David, can you put Bruno on?
I promoted him. David is no longer in now.
Okay.
Now the host is you and me.
Okay. So can Bruno please say something?
His internet is not so good, so I paid him to promote him.
Okay. Okay, good. So let me just continue now. I think we are going to spend a lot of time. So I hope people have downloaded the material for today. So I'm going to start off with where we left yesterday. So I asked you to go and open this R script that I sent you yesterday. Are you seeing my screen? Okay, good. Okay, so we are going to do the practical for the split plot and incomplete block design. There are a few questions that were asked yesterday that I did try to explain. The first one, that the difference between a factorial and a split plot ANOVA. So factorial, I yesterday tried to emphasize that a factorial experiment is an experiment in which two or more factors are being tested together. And one design that can be used for a split plot for a factorial experiment is what we call a split plot. Now, a split plot is where you have two factors. One is going to be assigned on a relatively bigger plot, and then that bigger plot, which we always call a whole plot or a main plot, will be splitted into a second into smaller subplots, and on the subplot a second factor will be applied. Now, the difference between the analysis of a normal factorial, where you assign a combination of factors, you assign a combination of factor on a plot, compared to a split plot, is that the main plot in a split plot has fewer number of replications compared to the ordinary factorial let's say compared to factorial experiment in randomized complete block design. So maybe let me just get my PowerPoint and then I try to illustrate this to make the point a little bit clearer. So I'm going to draw something here, then I will try to illustrate the point. So let's say we have two factors. We have variety, and in variety we have variety A and variety B. And then the second factor, let's say we have say fertilizer, and then let's say we have 0 kilogram of a certain fertilizer and 50 kilogram of a certain fertilizer. Okay, so from here, what we'll have is that we can, if we are to look at the different combinations, yeah. The script name is, I think, analysis of incomplete block design and split plot. Check the what we shared yesterday. So here you have, for example, fertilizer A without, you have variety A without fertilizer. You have variety A with 50 kilograms of fertilizer. And then you have variety B. B with 0, and then variety B with 50. Okay, so let's call this one here our treatment number 1, our treatment number 2, our treatment number 3, and then our treatment number 4. Okay, so now when we are going to assign our treatment to our blocks, this is how we're going to assign them. So what we're going to do in this case, we're going to have, this is our block. And then in this block here, we're going to divide it into 4 different plots. Plot 1, 2, 3, and 4. So here then we can randomly assign the four treatments. So let's say, for example, here you have your treatment number 3, you have your treatment number 4, say number 2 rather, you have treatment number 1, you have your treatment number 4. Okay, so this is our factorial with randomized complete block design, RCBD. Now with a split plot, the result is different. So with a split plot, what we have is that in this case, the first thing that we do is to first divide our plot into 2. So let's say this is our main plot factor, and this is our subplot factor. So the first thing that we do, we divide this into 2, and then we can, let's say we have variety B falling there and variety C falling, A falling. Okay, so this is the first level of assignment. Then the second level of assignment would then be to come back here. And then we split this one here now up into two again. So I split this into two, and then I assign my, say, 50 kilogram there. And then I assign my 0 here. This one I also break it into two. Let's say I assign my 0 here and I assign my 50 kilogram here. So the difference here is that the assignment is done at once. We do the assignment only once. Here, the assignment, the randomization process is done 2 times. You first randomize the main plot factor, and then you randomize the subplot factor. So that is the difference between RCBD, factorial design, factorial treatment structure in RCBD with factorial treatment structure in a split plot design. Somebody want to know the difference between a numerator and a denominator degrees of freedom. Yesterday, I showed you. Okay. So remember, when we are calculating F statistics, what we always do, we have this formula here. We have mean sums of squares for treatment divided by mean sums of squares for error or for residual. Okay. So I told you that I was taught sometimes very, very long time ago, if you have a fraction A over B, then this is what we call the numerator of a fraction. And this is what we call the denominator of a fraction. Okay. Now, when you go to analysis of variance table, treatment will have, you have a number of treatments. So the degrees of freedom that is associated with treatment is what we call the numerator degrees of freedom. And then the degrees of freedom that's associated with the denominator is what we call the denominator degrees of freedom. And this degrees of freedom is important if you go, for example, you want to compare what we say F statistics with F calculated, then you need to go and read from an F table. So in an F table, you need to have your degrees of freedom for the numerator and your degrees of freedom for the denominator. So that is what we actually have. Somebody wanted to know how to compute the denominator degrees of freedom. Now, this is not the best place to do it, but what always happens here is that from the analysis of variance table, it is always given to you. The only difference that when you're using the mixed model approach, like I tried to show yesterday, the degrees of freedoms are not whole numbers. They are always up decimal places, and this is because they're based on approximation. How do you differentiate the wrong and the right variety? No, I think that question cannot be answered now. It needs more clarification from whoever asked the question. Would it not have been wiser to have fertilizer and main effect? No, that one we can. That one now depends on you as the person who is doing, like I indicated before, what you put on the main plot is mainly based on the logistics of application, how easy it is to apply. And the other thing is also, it is based on, you need to sacrifice something. So if the factor that you're studying, one of the most, the factor you're studying is very important to you, it doesn't make a lot of sense to put it on the main effect, on the main plot, because it will be estimated with a very low precision. You say low variation within a treatment is good or bad thing. Okay, one thing, if you remember when we talked about, we talk about principles of experimental design, we talked about controlling variation in an experiment. So remember, what we are interested in this case is we want to have a relationship between the treatment that you're testing and and the response of, say, plant or animals or human being. So for you to study that relationship between plants, between treatment and then a particular characteristic or growth parameters, you need to be able to control variation that is not of interest in your study. So in terms of experimental setup, you want to minimize variation as much as possible. If you don't minimize variation, then you're going to get so much noise in your experiment that you will not be able to come up with a clear relationship between the factors that you're trying to study. Did somebody say, can I analyze split plot as a resolvable alpha lattice design? Why would you want to do that? That I already showed you that you can analyze this one here in different way. The only difference here is that you can use split plot to analyze both of them. Okay, and remember, once you set up an experiment in a certain format, it's important that you analyze it in that particular format. If you change the analysis, that means you are actually trying to cheat the system. That is not going to work. Okay. Any other question that? How does this apply to molecular biology, data analyzing diversity of structure or fungal microbe? Now, if you have some specific requests that you need to make, then you can consult one of the trainers so that they can be able to attend to you at some point at the later time. Because remember, we are now having about 500 people. So if we try to attend to each one of you, it's going to take us a long time to settle, but we will be able to help where possible. Under what circumstance does the split plot work? I think I've tried to answer these questions a number of times. Okay, so now let's first try now to run our scripts. How many people have got the script now? Have you got the script from yesterday? Okay, good. So I'm going to show you my script and then we are going to, somebody say you have not got, please try to get the link for today and check on yesterday's. Is the same link, then check in the folder for yesterday. Please share. Yes, somebody has already shared the thing. So let's do it quickly, please, so that you don't have to. Beleke, please get the link. Okay, I give you 2 minutes to please get the link and get the script so that we can start running. We have a lot of things to do. Okay, so let me just share my other screen. Okay, so the name of the script is analysis of incomplete block design. Please check. Okay, so I think we cannot overemphasize the importance of having a correct working directory. In most cases, most of the errors that we get in the analysis, especially if you have a script that's already written for you, the most common source of error is data cannot be found, which is because you have not specified the correct working directory. So I would request that you know the directory where your data is located And in that same directory, also we make sure you put in your script. Then the best thing to do would be to then direct R and tell R that, please, I want you to use this as my working directory. And how do we do this? I'm going to repeat that again. So please, you can go to session. Are you seeing my screen? Go to session. It's not adding anymore. Okay, so you go to session. And then from session, you select set working directory. And then you choose. So this one is say choose a directory. So you can see from there, you go to session app, set working directory, and then choose a directory. So for me, I'll click mine here. And then I can look for so mine is, I put it under incomplete block analysis. So if you're successful, the first thing is that there should be no error in your console. Like you can see mine, there's no error. And then the next one here, you should have this command here written, set working directory, then it gives you where the directory is. So I would expect that everybody has a directory where the data set is, and then from make that become your working directory, and then we can go ahead and do the running. How many people have changed the working directory successfully? Can I see some yeses? Okay, good. Okay, so then the next source of error is a particular function not found or a package not found. So there are issues here. The first thing is we need the package Agricole. How many people have already installed Agricole on their computers? Can I see? Okay. How many people have not yet installed Agricole? Okay. So for us to install Agricole, what you need is you just need to remove this thing here, and then you can run install.package Agricole. So the command that you need, this is the command that you need. So after you've installed the package, the next thing that you need to do, you need to use the word library and then put in bracket Agricole. So what I'm going to do, I'm going to run this. I don't see any red, so I'm okay. Another package that we need to install is, so what we need to move the S, and then, so we need to install package mass, because there's one of the data set that we're going to use is in the package mass. So how many people have installed mass? The script, you have not received the script, please, you have the script. Once you have the link, you should be able to how many people have not installed package mass? And please start again. Okay, install the first. Let's give a few minutes for the mask to be installed. So please get the link for today and Mona, can you install the process? Can you install, please? Those who are saying no, I want you to install the package mask. Use the command that I have given you and run it to install it. If you don't install, next time you try to use the function, it will tell you it is not there. So after installing, the next thing that you need to do is you need to run this line here. When you're running this line here, you're bringing now the package ready. So we can run library mask. I click on that. I have a warning. So it's telling me the package mask was built under R version 4.0.5. Okay. The next package that we need is Malcolm. So Malcolm is used for multiple comparisons. So you also need to install the package Malcolm. So what you simply need in this case is remove this, and then you click on it, then you run. So you can highlight it also like this, then you run. I gave you this thing yesterday. I expected you to have at least run it throughout in the evening. I know some of you could have done it. So how many people have installed Malcolm? Okay, good. So I'm going to give 1 minute for those who have not yet done. Okay, so after you've installed the Malcolm, the next thing that you need to do, you need to call it in using the library. Okay, so you see a few reds there with a warning, but that warning is okay. And then another package that we need is lemma test. I showed you yesterday how these things were done. So if you have not installed, remove this, and then you have this line to run. Okay, so after you've installed, you can call it now in and you'll be ready to work. And finally, you need, I know all of you have ggplot2. So I think you can also do the ggplot2. So we have library ggplot2. Okay, so if you've done all this one here, that means you are now ready to start the analysis. So I'm going to repeat the same explanation I had yesterday also today, but at least this time with the data in. Okay. So the first thing that we are going to do, we are going to see how to generate the split plot design in the field. So a split plot has two factors. One factor will go on the whole plot, that is on the bigger plot, and then the other factor will go on the subplot, that is the smaller plot. Somebody said, I'm too late joining this training. Could you please help me how I can equally proceed with that? Oh, one of my colleagues will help you for sure. Okay, it's never too late. So we will still go on. Okay. So the first thing that we do, we create a vector, and this vector will give us the three variety that we are testing in this experiment. So what I do, I click on this. Okay. So if you don't have any red, that means you've created now an object called all plot. And what you can simply do, you can just type the name in the console, and then you click the enter button. It will tell you that what you created a vector with 3 elements. The first one is called golden red, the second one is called marvelous, and then the third one is called victory. The next thing that we need to do is to create another object. This object now is our fertilizer, the one that is going to be our subplot factor. So when we click on this, you've not seen any red, that means you're okay. So we can simply we just type subplot. And you see now it even gives you suggestions. We click on that, then it tells you you have 0, 0.2, 0.4, and 0.6. Okay, so what we have done here, we have created an object that represents our variety, the variety that we are testing. Here we have an object that represents the fertilizer levels that we are testing. And then we are going to use this nice command here, design.split, to create for us our split plot design. Okay. If we run this, so if you don't see any red, the only red you're likely to see here if you're running my command is telling you that this function doesn't exist. If that is true, the case, that means you did not install the agricole, or you did not call the agricole command, because agricole package has the design.split function in it. So you need to call it in order to be able to use it. Okay. So now what we can do now is with this command here, now we can look at the field book, what we can actually go with it to the field now to set up our experiment. So this is the object that we produced in our previous step. And then you put a $sign here. You're telling Ara that please go to this object here and pick for me what we call a book from it and print it for me. So I'm going to go here. I click on this, and then I have the things there. Okay. So with this, you are now ready to go to the field. You know that your plot 1. So you have these 3. Okay. So we have block 1. And then this is the big plot that has golden rain. And then within the golden rain plot, we split it up and then we randomize the subplot. So this is actually what you can go with to the field and for your field setup. So can I ask how many people have run successfully up to line number 18? Can I see some yeses? Error. So which error did you get? Somebody said error. What did you get? If you've got an error, please put the error that you've got. I'm sure the error should be related to the design.split. Okay, you put the design in the Q&A and somebody will get for you. SP design not found. That means you did not create it. You first have to create it before you can find it. So did you check my line? Did this line here work? Line 16, did line 16 work? Subplot object not found because you did not create it. So if you don't create it, there is no way you can find it. Okay, so I can assume now, okay, perfectly working, that is fine. Line 16, explain line 16. Okay, so line 16, for you to run line 16, the first thing you need all plots. So you should have created it. If you don't create it, then you cannot run it. So we need to get what we are going to put on our whole plot. You also need to include what you put on your subplot. Then you need to specify the number of replication is 6. And then the design here is RCBD. So you run a randomized complete block design. And then here the series is 1. Seed is 10, and then kind is super duper. Okay, so some of these you don't need actually to worry much about. So, but what we want is that yes, somebody say could not find the design.split. That means you did not install Agricole. You first need to install Agricole and then you call it. If you don't do that, then you will not get. So can you please install Agricole? Once you install Agricole, so you need this command here. You need to install Agricole, and then after that, you need to call it. Okay, so I'm going to proceed. How to create the subplot? The subplot is created here. Look at this command here. Can you run every line of my command just the way it is? Then you'll be fine. So when are you supposed to use the $sign? What we first need to do is, if you want to learn R well, you first need to be able to run a simple command that is given to you without touching it. Okay, first run a line that is given to you without touching it. Once it can run, then you can start touching it. Okay, otherwise you're going to be in problem. Okay. Okay, so the next thing that we are going to do now is we are going to, you are told that in R, there are a lot of data sets that you can actually use for playing around with if you want to do to play around with. So what you need is you need to call a particular data set. Now we have okay, so please, if you have any comment that you want to be addressed, please put it in the Q&A, because if you put it in the chat, there are many things that are put in the chat and it will disappear before they can pick it. or can be responded to. So what we want is we want to get a data set. This data set is called HOTS and it is found in the package mass. So what we are going to do, we are going to run this line here. Click on that. Okay. So line 20 will simply say, get for us the data set called HOTS from this particular package. And then line 21 will help us. Line 21 will help us to see the structure of the data set itself. So here it will tell you that this is a data frame. It has 72 observations of 4 variables. So the first variable is B, which is a block. So here you have 6 levels. So you have block 1, block 2, up to block number 6. Factor 2 is called V. It has 3 levels. You have the golden rain, these are the varieties. And then factor N has 4 levels, the 0.0 CWT, 0.2, and so on. And then the last value here is yield. It has these values here. Now, please note here, somebody talks about the dollar sign. You see, the dollar sign can be used to extract a particular variable from a data set. Okay, so we tell you B is a factor, V is a factor, N is a factor, but Y is an integer. That is what we have here. So we can also look at the dimension of the data set that we have. So the dimension will give us the number of rows and the number of columns. So here there are 72 rows and there are 4 columns. Now what I want to do now is that I want to change the names that are present in this data set. I want to create my own names that I think is easy for me to understand. So I can change and say, well, the first column you call it block, the second column you call it variety, the third column you call it nitrogen, and then the last column you call it yield. So that is what I'm instructing Ara to do for me. I'm telling Ara, please go to my data set here, which we call odds, and replace the names that you find there. Okay, maybe before we run this command here, let me just type this. I want to find out the existing names now. So I say names, I put in the HOTS, I click. So you can see the names that I have here are, we have B, we have V, we have N, and then we have Y. So I want to change this one here so that I have B stand for a block, V stand for variety, N stand for nitrogen, and then Y stand for yield. So what I'm going to do now is I'm going to change the names. So okay. Somebody said we thought it is split plot. Why using RCBD in line 16? Of course, split plot, as I indicated on the first day that I talk about experimental design, split plot is how you arrange a factorial treatment on to your experimental units. And one way of doing so is, okay, split plot can be used with completely randomized design, with a randomized complete block design, with a Latin square design, even with incomplete block design. So split plot is more how you put your trees, how you put your treatment, lay your treatment onto your experimental material. So it still has RCBD, so don't get surprised. Now, so we can look at the new names. So here you have instead of the previous name, B now I have blocks, V now I have variety, N now I have nitrogen, and Y now I have yield. So this is what we now have as our new name. It's also important to actually ensure that the names are, you know, the right name that you're using. R is case sensitive. So block with capital B is different from block with small b. I know you've just had your Valentine yesterday. I assume if you call your partner the wrong name, I assume you see the kind of fight that can come out in the house. So ARA also does the same thing. It will give you red straight away if you put in the name of something that doesn't exist. Okay. So what we have done so far is we have looked at a data set that we want to, this is a data set that we are going to use for our analysis. I put it as so I can look at the structure again, and then you see now I have blocks here now. Now I have variety. Now I have nitrogen, and now I have yield. Now I want to show somebody who say, how do I, when do I use a dollar sign? So for example, I want to see what is in, so this is my data set, it's called odds. If I put a dollar sign there, now you see I have options here. Do you want to show the yield in the data set? Do you want to show the nitrogen? Do you want to show the variety? Do you want to show a block? So I can click on that. So then it tells you, this is what you actually see: block 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3, and so forth. So if I want to extract only one small thing from my data set, I can use a dollar sign. But as Ellen also told you, I can also use a column. For example, I can say, take for me column number 1. It gives you the same thing. Okay. Okay, so I assume you already got your library ggplot. I can run it again. The first line 16 and 18, the package is Agricole. Okay, so now I want to just draw some simple graphs. Now, the first thing that I always, if you want to learn, you have the script. The first thing is don't touch the script, run the way they are, okay? Once you're actually done with running the way they are, then you can now start touching, okay? So the first thing, let's first run the script here without disturb, then I will explain to you what I'm doing. So the first thing that I've done is I've created an object called plot 0. And how did I create that object? I used a ggplot to do that. Now, in the first, I will telling ggplot that on the x-axis, please plot my nitrogen levels. On the y-axis, please plot my yield. And then the data that we are using in this case, we also specify that the data is also hot. So this is actually will give you those ones who, this will give you a blank, like a canvas to, if you people who do painting, you have a canvas. Now, the next thing that I'm going to do is that, remember here, I told that on the x-axis, I want to have y, to have yield. And then on the y-axis, I want to have y on y, I want to have yield. Now, somebody said error. Object not found. Did you put data in the bracket? Okay. So the next thing that we are going to do is we're going to run the second line. So the second line now tells, it gets for you the canvas that you've drawn, and then it puts for you a box plot on it. They call geo box plot. So this one here, it puts a box plot. Okay, it puts a box plot. So we are creating a new, but you see now what we are creating is we are building on what we already have before. We build this, we created that object. We bring that object here, we add something to it, we create a new object of the same name. So we move in there. The next step that we want to do now, so with this one here, if at this point now, I decided to see what I have, I can print this. So at this point, what I have is that I have nitrogen at 0, I have at 0.2, I have at 0.4, I have at 0.6. Okay, so that is now from this particular point here. The second thing that I want to do now is I want, by this using this wrap, Factorial wrap, what I want now, I want to see to have this box plot now, but for each block separately. So I can run this. Let me first print it to you to see what we have done. Okay, so now we have it for the different blocks now, separately. The next one is, then we say you want to get the theme. So let me run this and also you see what will happen. Did anything change? So with the theme, you can, this is like back, I mean, the background is black and white or what you have here. So as you see from here, we start building our plot by just creating a blank canvas. If you run this first step here and you print, you will not see anything because it just prints a blank canvas with the x-axis having nitrogen, y-axis having yield, but it has not. You've not given it what kind of graph to draw for you. In the next step, you tell them to draw for you box plot, and then in the next step, you tell it to say, well, you draw for me box plot for each block separately, and so on and so forth. So this is what you have. The likely error here is the error that is associated with not having the data and the error associated with the ggplot function not found. These are the two likely sources of error. Johanna, where can I find you? Well, but can you run the scripts? If you can run the script, then that's fine. What we do. So let me just repeat here a little bit what we are doing. What we simply want to do here is we want to draw a box plot, and the box plot that we want to draw is yield versus nitrogen. Okay. Now let's get you on the plot, and then we go before plot later on. So before the plot, what we did here, what we are simply trying to do here is we are simply trying to get a data set from R. And for us to get a data set from R, we need the package mass, because that's the package that has that example data set. So with this step here, the data set now becomes available for you to analyze. So the next step is we decide to say, let's look at this data set here, which we call HOTS. What is it like? What are the different components? So what we did here, we ran this, and then it tells us that this is it first tells you that this is a data frame, and it has 72 observation. It has 4 variables. That is what we have here. And then the variables are, there is the block, which has 6 levels, is a factor with 6 levels. We have a variety, which is also a factor at 3 levels. And then we have nitrogen, which is also a factor at 3 levels. Okay. But that was what we have. So if we start from here, then this is what we'll have. The next thing, we ask for the dimension, and then it says 72 by 4, and then we change the name of the, instead of having B, V, N, and Y, we change the name. So we change it to that, So when we get this, we now have different names altogether. Okay. So the next thing then is to call the library ggplot2, which we already did before. And then here we are trying to do a box plot. So the first thing that we did in a box plot is to create a blank canvas. I create it here. If I print this, it give me blank, because what I have is I just have a canvas. I've not yet put anything on it. I've only tell Ara that on my x-axis we are going to have a nitrogen, on the y-axis we are going to have yield. So the next step then is on the canvas that we have, we now draw something. We can print and see what we have drawn. And there we go. Okay. Then the next step, we said, well, we want to see for each block separately. Okay. So we go in here, we run that. We can print and see what we have done. Okay, so we go there. There we go. Then the next thing we go is we want to look at we can print also that, and there we go. I yesterday explained exactly what's going on within there, okay? Okay, I thought I explained this box plot yesterday. Okay, I'm going to try to explain and see. So what we have here is then that, so we have here is for block number 1, block number 2, block number 3, block number 4, number 5, and block number 6. Okay, so if we look at block number 1, we have here, I don't think now I cannot zoom it anymore. Okay, they're not seeing it. Okay. Zoom, resume. Zoom in. Okay. Okay. Check whether it's okay now. Okay. Okay. So what we have here, okay. So here we can see where we did not apply fertilizer. The yield was around, the mean yield here is around 100 and say 10. And then the median, then where we add 0.2, it moves to 25, 125, above 125, and then 0.4, and then and so on and so forth. From here, we can also tell that where we did not apply anything, there seems to be small variation between the different varieties, the performance of the different variety. But where we put 0.4, there seems to be a wider difference between the performance of the different variety. So the different varieties appear to react differently to our fertilizer. But if we look here, for example, we see that there seems to be a linear relationship between the amount of fertilizer that you apply and the yield of the crop. We seems to see an increase here. The same pattern seems to also be here, but in block number 3, we seems to see something like it rises a bit, then it starts dropping again. So there's some kind of a curve that we can see. If you're a soil scientist, or you're an economist, you talk about the rate of diminishing return somewhere along here. So something is happening within that. So what happens, so what we need in this case, the information that you can get from here is you want to see actually the trend in your data set to help you in when you come to confirmatory or inferential data analysis. I think. Okay, so we can do the same thing. I'm not going to explain for the for yield now, for the variety. So it's the same thing here. How do we determine the factor levels? The factor levels now is an expert determine. If you're a soil scientist, you're trying to do an experiment involving fertilizer. So there are different reasons as to why you choose a certain range of fertilizer to apply. Of course, you want to test the range that is sensible in terms of what is currently being applied and so on and so forth. So this question depends entirely on you as a specialist, as a specialist in either soil science, whatever. So for different selection of the level of factor in different studies will depends on the expertise in that particular field. A statistician can only advise you on what to do. If you want to look at trend, then you probably need to have at least 3 levels or 4 levels, then you can test that. How do we create a canvas? The first step here is how to create a canvas I talked about. So this is the command that creates the canvas. Then you're going to build onto the canvas. So we can go this, this, and this. Okay, so here you can see that block 1, it seems to, you see these two varieties seems to, they have actually very similar pattern. Golden, Rain, and Marvelous, there seems to be a slight difference. Victory seems to be more high yielding compared to the 2, but when you go to block number 2, things change. You see now Victory seems to be the lowest yielding compared to the other 2. Now, if you go to block number 3, is also a different change here now that Marvelous seems to be performing better than the other 2. So here, for example, you can see this pattern going a bit down, like the IS is the Golden, Rain, then there's Marvelous, then there's a Victory, and so on. So this will give you a rough idea what is really going on within your data set. Okay, the next thing that we are going to do, we are going to do a small block, a small line graph. So I'm still, the first line here is just to create the canvas. It is not plotting anything. You're just telling it, this is what I want to plot. This is the data. And then, so here we have our blank canvas with nothing in it. Then I can build my layer on the canvas. So if I print this, I don't see anything because it's just an empty. Then the next thing I'm going to do, I had now, GeoLine will give us a line plot. So if you plot here, you'll actually see. Okay, so you see some kind of zigzag lines and what going on there. And then the next one, I can plot for the different blocks separately. So I can see exactly what I've done before I add the next layer on it. And then I can finally go to the next step, and then I can do the last one. Okay, so you can see from here now that I have a plot between nitrogen and yield for different varieties for different plots. So you can see how beautiful the plots look. You can do this thing very easily in R. Other program, you'll struggle to get it. One of my favorite package is GenStat, but GenStat is very poor in graphics. So for R, I'm always at home. So so see what is happening here. Look at plot number 3. You see the performance of Marvelous seems to be above the performance of the other 2. Now, when you come to this one here, we have Golden Rain seems to be performing better than the 2, but the difference, we don't know whether the difference is statistical or not. Okay, so the next thing that we reach now is we want to now do analysis of variance. And this is what we are doing here now. We are doing the normal analysis of variance, assuming that we have done a factorial experiment in randomized complete block design. That's why here you have a block effect, and then here you have the variety times nitrogen, and then here you have your data, which is the HOTS. So that is the simple program that you have. So we can fit this. So what happened in R is that analysis in R is not is step by step. The first thing, you create an object, and then you can continue to do further analysis on the object. So we created an object called fit.aov. Now we want to get a summary from this. If you want to get a summary from this, okay. Okay, so here we have our block with 5 degrees of freedom. This is the sums of square per block, the mean sums of square, and this is the F value. Let me just rerun this first. Okay, so what I wanted, I tried to squeeze this side here so that I can have a longer thing on this. So here you have your normal analysis of variance table. I yesterday pointed out that the degrees of freedom for all these ones are okay. The only difference here is now that the degrees of freedom for the residual is 55, and this degrees of freedom is used for testing block, testing variety, testing nitrogen, and testing the interaction between nitrogen and fertilizer, nitrogen and variety. And that's where we have the trouble in that. Remember these two, the block and the variety, we did a different randomization for the variety within the block, and later we came and did another randomization for nitrogen and nitrogen, and then the interaction within the word. So this is how a normal analysis of variance table would look like. But yesterday I explained to you why this is a wrong analysis, especially for testing testing the block and the variety. Then we have another correct analysis here, which, oh, there are two. I think first run this one here. Okay, let me first run this, then I run the other one. So this is the one that is run using sp.plot. So sp.plot is a function in the package Agricole. So if you don't call the Agricole, you will not be able to run this. It will show you an error. So we're going to run this. So this one here will give you two different analyses. So the first thing that we have here is it will analyze for you this part here. Remember, we have 6 blocks, so the degrees of freedom is 6 minus 1. We have 3 varieties, so the degrees of freedom is 2 minus 1. Now, in this analysis, you have two errors. You have here error number 1. Okay, so error number 1 will be used to test for the block and test for the variety. And the degrees of freedom for error number 1 is 10, not 55 like we had before. Remember, in the first case, 55 was used as a degrees of freedom for testing both the variety, for testing both the block and the variety. But in this case, we have a special error. So this is error for the main plot. And then the error for the subplot is error B, who now uses a degrees of freedom of 45. Remember, these two initially were combined together, 10 plus 45 to give you the 55 that we saw before. Let me show you. So remember here, the degrees of freedom here was 55. So the 55 had 2 parts. There was a part that is for testing these 2 with 10 degrees of freedom, and a part that is used for testing these 2 with 45 degrees of freedom. That is the value. Okay, are there any question that? Okay. Okay, of course, we can get the same correct analysis by assuming that assuming that the block effect and the block or the interaction between the block is random. So we need to use this function here. So this function here is part of LMEA test package that we also install. So I go up and I show you why we install this package here. So it is part of this package here. So if you don't have this package here, then it will give you an error when you try to run the other one. So we can run this. And then we get the summary. Okay. To summarize. How to export what? Okay. Okay. So here, when we look at this alternative using lemma function, it gives us what we call type 3 analysis of variance table, and then it gives you with this Gensmonth method. Yeah. So if we see from here, we have the sums of square per block, the mean sums of square. Then here you have the numerator degrees of freedom, which is 5. That is the same as what we saw before. And then the denominator degrees of freedom is 10. So here, the error degrees of freedom is 10. And for variety, the error degrees of freedom is also 10. That is what we saw in the previous plot. But for nitrogen, you see here the error degrees of freedom is 45. And then for the interaction, the error degrees of freedom is also 45. So those are the things that we have, but they give you the same result. So the mixed model analysis result and then the speed dot plot results are the correct analysis that you need to do when you're doing split plot and not the other one. Somebody asked, how do we get a plot from ARA? How do we get a plot from ARA? Of course, if you look here, there is what called export. So if you click on the export, there are options here. You can save as image, you can save as PDF, you can save as clipboard. But I remember very well on the first day, Ellen showed you some sophisticated method of doing that, where you can get directly, you can also send this one directly into a document, into a PDF, and then it gets printed there. So there are many ways of doing the same thing. To me, my advice to you at this point is, let's get the basics right. Once you have the basics right, you should be able to explore some of this thing on your own, and you should be able to get on quite well, okay? I just want to run the remaining one so that I don't consume all the time for my colleagues. So the next thing that we need to do in this case is we need to do the analysis of incomplete block design. So I gave you a data set. This data set is called bibdata.csv. Please check in the folder and ensure that it is in there. Can you check, please, and tell me whether you have it? Do you have the data? Okay. If you have the data, that is good. Now the next thing is the data where? Is the data in the working directory? Is the data in the working directory? If yes, then we are good to go. If no, then you're going to get error. Okay, so I assume that you are there. And I also personally assume that I am there. So let me run. If I get red, that means I'm in a different folder. Okay, I'm not got red, so I'm okay. Okay, so once you've called that successfully, that means you have the objects already with you. So the next thing that you need to do, you need to check the names. What are the names of the variables here? So mine I have block, variety, yield. Okay, I'm going to clean my console. Okay, I've cleaned my console now. We are okay. Right. Okay. So the next thing that we need, we got the name. We can look at the dimension. It started by 3. We can look at the structure. Okay, so something is important here. So look here. Here it's a data frame, which is okay. We have 30 objects, observation rather. and 3 variables. So what are the 3 variables? We have a block, and the block is an integer. So it reads as 1, 2, 3, 4, 5. We have variety, and the variety is also an integer. And then we have yield. But for us to do analysis of variance, we need these two to be factors. So we need to convert them into factors, okay? So the first thing that we are going to do now is I'm going to use this command here. See what I'm doing here. So I'm saying, go to my data set, which I call BIP data, pick out what the column that I call block, and then replace it with the same thing, but this time make it a factor first before you replace it. So once I do that, I run this, is there, okay? And then the next thing I do, I said, please go pick my data set there, pick what I call variety, please replace it with the same thing, but this time make it a factor. So here I run this line. Okay, so the next thing then I can look at the structure. So I made changes to my data set. Let me see what changes I've made. I click on this, then it will tell me, okay, let me clean my console before somebody complains again. Okay, so here now, my block now is a factor, okay, with 10 levels. Now, my variety is also now a factor with 6 levels. Now, my yield remain an integer, so that's okay now. We can do the analysis. I just want to show what is present where in my arrangement. So I want to show the field, the distribution of the different varieties in my balancing complete block design. So you run the line. Okay, so this is what we actually have. So these are my varieties. Remember, we have 6 varieties. Variety 1, 2, 3, 4, 5, 6. And then we have 10 blocks. So block number 1, number 2, number 3, up to number 10. So what this is showing us that in block 1, the first 3 varieties occur in block 1. So there's variety 1, variety 2, variety 3. There's no variety 4, no variety 5, and no variety 6. When you go to block number 2, you have variety 1, variety 2, and variety 4. When you go to 3, you'll have variety 1, variety 3, and variety 5. When you go to 4, and so on and so forth. So this is what the summary of where the different treatment occurs within your experiment. So we can still go ahead and do the box plot like we did before, but I don't think we need to look at the content anymore. It's the same thing. I can also draw the same thing using so let me just expand this a little bit. So this one just shows us where the different varieties are. Okay, so now let me try to slow down a little bit, and then I finish up what I'm doing here before I give you back to my colleagues. I know my voice is not as smooth as their voice, so I better get out of this place before you before I bore you to death. Okay. So here I am going to do the intra-block analysis. Yesterday I talked about the intra-block analysis. So with the intra-block analysis, what we are trying to do in this case is that we are first going to remove the effect of the block before we analyze the treatment effects. So that is what we call intra-block analysis. And the intra-block analysis will use what we call a type 3 sums of squares. So here I'm creating an object which I call fit.yield, and I'm using analysis of variance. So this is my response variable. I call it yield, and then this is a Greek letter called tilde. So I want to have block as one of my explanatory variable, and then variety. Then the data here, in this case, I need to give the name of the data. The data here is BIP data. Okay, so this first step here will run for me my analysis of variance. It's like the ordinary analysis of variance. So the second step now will analyze, will subject what I've got here to an analysis. And in this case now, it provides analysis, provide for us what we call the type 3 analysis of variance. So say drop one, you run this. Okay. Okay, so this one tells you that this is a single term deletion. So this is the model that we ran. This is our analysis of variance. So we remember there were 10 blocks, so the degrees of freedom is 9. We had 6 varieties, so the degrees of freedom is 3. And then we have the sums of squares. And then you have here our F value, and then we have the statistics is here, is what we have down here. So from here we can see that VIP data doesn't need a package. What you need is you just need the read.csv. I think I will show back the comment again. The line that is used. You need read.csv. You're reading it from a file that you already have. Okay. So this is our analysis of variance table. At the end of the day, you have your p-value for the variety, and in this case, the value is less than 0.05, so it's significant at 0.05%. Let me try to squeeze this one a little bit so that I can have a better view. Okay. So this is the whole thing. So here you have some kind of, you still have the F value, but it also gives you what called the AIC, which is another way of testing the model. So for now, let's just stop at this. We have this significance, and then we can proceed with the next line. So this is the next thing that we can do is to run some kind of Susan talked about a contrast yesterday, so we could actually run and see what will happen. Okay, let me just show you what is happening here. Okay, so this is kind of testing for you. You're doing some kind of pairwise comparison. So here you're looking at the difference between variety 1 and variety 2. You're testing the hypothesis that difference is equal to 0. This is the actual difference between them. You have the standard error, you calculate a t-value, and then you have the t-statistics. So from this, we see that variety 1 is actually significantly different from variety 2. Then we look at variety 3, significantly different from variety 1. Variety 4, significantly different from variety 1. Variety 5, also significantly different from variety 1. But if you look at variety 3 and 2, variety 4 and 2, they are not significantly different from each other. Okay. So the rest actually are not significant. So what is happening here is only variety 1 that is different from the rest. The rest are all equal to each other. So that is what you actually, this analysis can give you, okay? So that is what I call the intra-block analysis. So here, a block is considered to be, if the effect of the block is considered to be fixed, and then we first remove the effect of the block before we do the analysis, and then we do the interpretation. The next thing is we went for what I talked about, interblock analysis yesterday. So the interblock analysis, now we use also the lemma function, and this one is from lemma text test that we already have. If you don't have, it will make noise for you. So here we're still fitting a similar yield with variety. Now, when it comes to the block now, when you put a 1 and then you put this and then you put a block, what you're saying is that you're declaring that a block effect should actually be random. And that's where now we have what we call a mixed model, because here variety effect is considered to be fixed. The block effect is considered to be random. You have two different effects in the same model, then it's called what we call a mixed model. So we can also run this and see what we get out of it. So this one gives us a similar results like what we had before. You can see one is actually significantly different from the other treatment, but then not the other ones are not different among themselves. And then I will just show you the analysis of variance itself. Okay, so this is the analysis of variance itself. When you ask for analysis of variance, it gives you a smaller part of it. It gives you only the variety, which is the fixed effect. And then so it doesn't give you the residual, it doesn't give you any other, the block or what. Now, if you want to get the block, then you need to ask for the variance component, which we are going to see later, okay? And then the same analysis yesterday, I told you can also use this function here, bib.test. Okay, let me see. Bruno, can you stop raising your hand, please? Which data type in R can be converted to factor? Any data type can be converted to factor. Levels of levels attributed to factor. I don't understand the questions. If other package does not accept read or CSV, other package will always receive that. But you can have your data in different format. You can have a text format. You can have Excel format like you were shown before. So you don't need to have that. Somebody said the current message I am getting a version of this package for your version of ARA might be available. So that means you need to update your ARA or you follow that link and picked it from there. Could you explain the box plot generator? I think I did that. Okay. Okay, so let me just do the last part, which is that and the balance, the alpha lattice design. So with alpha lattice design, we need another package. There's another package called AgreeDat. So AgreeDat package is a package that has examples of agriculture. There are a lot of data in that. So can I ask you to install this package here called AgreeDat? Have you installed the package? Just run that, and I see how many people have installed. Okay. Good. Okay. So after installing, then we need to call the library, AgreeDat. So here we are again getting another data set from R. And this data set is called John.alpha. So it's an alpha lattice design data set. It's also on HOTS, I think. So what we want to do is we already have it there. Now we want to call it, to create an object called that, which we give it the same name. Is easier to type this one because just three letters. So we can create that. Okay. So now we can look at the structure of this data that we are trying to analyze. So use TSTR. That stands for structure. So from here, you can see that we have, this thing is over disturbing me. Yeah. Okay, so it's telling us it has 72 observations with 7 variables. The first variable is a plot, which is an integer. The second variable is a factor called rep. It has 3 levels, rep 1, rep 2, rep 3. The third one is a block with 6 levels. And then the fourth one is gene, which is genotype with 24 levels. And then you have yield. Okay, so that's the data set that we have. So the next thing that we need to do is we need to see how best we do some exploratory analysis here. So we do simple box plot. So let me just try to zoom it. And then I stop and share. Okay, so these are the box plot for our 24 genotypes. So some of them, like this genotype here, it doesn't vary at all. Some of them have a lot of variability in them. They have different yield. You have high yielding one like this one here. You have very low yielding one like this. But as you see, the value run from 3 to around maybe 6. So these are the different things that from here you should be able to actually start telling part of your story. We can do the same thing for the rep. So you can tell what is happening in your replicates. Okay, so you can see that replicate number 3 seems to be slightly low yielding compared to replicate number 1 and number 2. So this could also be replicate that's found in a less fertile area compared to this other 2. But you also look at the variability. Replicate 1 seems to have higher variability compared to replicate number 3, and then replicate number 2 is somewhere in the middle. So that's the kind of information you can pick easily from your box plot. We can also look at the blocks. Remember, the block is an important thing in our case here. So we want to see, are these blocks really, are they different? So you can see that there's block number 6, which is highly variable. The performance of the different variety in block number 6 seems to vary a lot. But in terms of the mean, the block seems to be similar in terms of the mean. So maybe blocking may not really be that useful in this particular case, but you do the analysis and you check what can actually come out of. Okay, so then the next thing now that I'm going to run just a few more slides, and then we look at we interpret the results, and then I can hand over to my colleagues to continue. There's so much to talk about that we cannot exhaust it within a short period of time. So that's why I think it's important that we continue offering this kind of courses from time to time. So probably what we are going to do, I saw somebody put up on the chat that maybe we need to separate the beginners from those ones who are there. So we maybe now after this, everybody will no longer be a beginner. So next time, a criteria for going for an advanced course will depend on the certificate for this course here that we are going to give you. So you need to work hard and make sure you go with the certificate, so that next time we can now promote you to senior, to P2, primary 2 or senior 2, depending on how you feel about yourself. Okay. So now we are going to analyze this as randomized complete block design. So as randomized complete block design, let me bring back the plots for the replicate. So what is going to happen in this case is, I'll share this first. So what we're having in this case is that we have 3 different replication: replicate number 1, replicate number 2, replicate number 3. And this replication here now, we're going to analyze them in randomized complete block design with 3 replications. So, and we're going to see what kind of result you will get. In this case, we have ignored the effect of the blocks. Remember, the blocks are now smaller units that are combined to form a replicate. So in this case, we are ignoring the block. We assume that we are running a randomized complete block design with larger numbers of blocks. So we can run this. Okay. So what we have here is we have a completely, this is how a randomized complete block design output looks like. So we have 24, we have 25 genotypes, so the degrees of freedom is 24. We have 3 replications, so the degrees of freedom is 2. And then, so here we can test and we say, well, genotype is significant, replicate is also significant. Is the degrees of freedom based on the size of the box plot or the media? The degrees of freedom is based on the number of replications that you have, the total number of observations you have in your study. It has nothing to do with the box plot or the median. Thank you. Okay, so here we assume that we are running randomized complete block design with 3 replication, and this is the kind of results that we get. Sometimes the difference between the different approaches may actually be very small, but for statistician, it means a lot. So here we are running a second model. In this case now, we are using now, so here we're saying blocks are nested within the replication. Okay, so here we still have genotype being significant, replication is also significant, and then we're also saying that there is actually substantial variation of blocks within each of the replicate. Within each of the 3 replicate, the blocks are not the same. So the issue of analyzing it as randomized complete block design may actually not give us a complete picture of what it's supposed to be. So this analysis here that we have done is what we call this is the intra block when it is the fixed. The block is fixed. So this is where now we assume a linear model, a linear mixed model where we combine the intra and the intra-block information. So this is going to be a different result from the one we have previously. And then finally, we are going to combine those results together, and then we are going to see how things will work out. So here we can. Okay, so this is our third results. And in all cases, we have significant genotype. The replicate is also significant. The other thing that we get from here that we don't get from the other one is we can get what we call the variance component. So the variance component, this is going to estimate how much variability is there within the block. How much variability is there between the blocks within a given replicate. I'm going to skip this one for now because when I'm going to come to mixed model, I'm going to talk about the variance component. So for now, I would beg that I skip this, and then I'm going to show, I'm just going to illustrate the importance of what we have been doing by comparing the estimates of the mean from the 3 different model that we have above, so that we can see what can actually go wrong in case you select a different wrong analysis. Break, okay. Okay, so this is what we have. Now, this is our genotype number 1. If we use RCBD, this is the mean for genotype number 1. Is 5.20. If you use interblock, you use the mixed model, you get 5.26. The difference is not much, but there is a difference. And then for intra, you get 5.14. So you can see that there is actually some difference. And well, it may not be much, but in some data set, the difference may actually be there. So it's worth doing the analysis the right way, because if you don't do it the right way, you're likely to end up with estimates that are different. You see, for genotype number 3, there is actually substantial difference from 0.838 to 0.335. So this is 3.3 to 3.5. So you can see that you have a higher value of the mean in this compared to this. Okay, then followed by that. So this is just to show exactly what can actually go wrong. So I think for now, we can stop there. I can answer a few questions and that then I will give you a small break and then we come back after the break. And say, why do I use this? Now I don't know how to explain it in the simpler way now. I need to take a cup of tea first, then I can explain it better. Okay, what is happening here is okay. When you're drawing a model, you can actually have, this is like the overall mean. This is going to be estimating for us the overall mean, but let me not do it now. So let's first have a break. I can answer that question later. Let me check whether there is any other. That Christine variation. Okay, I think somebody's trying to help. Let me see Q&A. Okay, so let's have a 10 minutes break before my colleagues can come in. So we are coming back at 12:12. So 10 minutes from now, please. Ugandan time.
Hello, hello. Are we back from the break? Can we start the next session? Good afternoon. Let me see in the chat. Yes. And welcome back from the break. Hopefully you had a good time with Dr. Thomas. Okay. So we are switching goalposts. We are going to look at correlation and regression. And if time allows, my colleague will come in with model building and regression. My colleague, Dr. Helen. Okay, so let's start. Is my voice clear? Is it audible? Do I need to increase the volume? Okay. Okay, thank you very much. Let us start. So we are going to look at correlation and regression with R. We talked about correlation the other time when I was talking about exploratory data analysis. So we are going to talk about correlation briefly. Correlation is a measure of degree of linear association between two variables, and it varies between -1 to +1. Positive correlation, you notice that in a scatter diagram, positive correlation shows values or plot points running from the bottom left to the top right. And negative, the points are running from the top left to the bottom right. Where there is no correlation, it is just a random scatter of points, as we shall see later. Correlation is a method for determining the type and strength of linear association between two variables. So the type is whether it is linear. The strength is measured by the magnitude. So if you have a correlation of 0.5, we would say that that is a moderate correlation. Anything above 0.5, then it would be strong correlation. Anything below 0.5 would be weak correlation. And if correlation is negative, then we say it is negative, either weak or strong correlation. And if it is positive, we would say the correlation is positive, strong, or weak correlation. So I've just said that a positive value indicates positive correlation and a negative value indicates negative correlation. So correlation coefficient of R, small r equal to 1 for a data set indicates perfect positive linear correlation. And if it's -1, it indicates perfect negative linear correlation. While R is equal to 0 indicates no linear correlation. We use a scatter plot to show us the direction, and also we can tell roughly the magnitude of correlation. To quantify the strength and direction, in bracket positive or negative, linear relationship between two variables, we use Pearson linear correlation. That is, if the two variables are continuous. If they are not continuous, there are other types of correlation like Kendo tau B, which can be used for rank data. So if you want to compute by hand, then we see that formula there. You can use it for computing the correlation. Sx is the sum of squares for x values, and Sy is the sum of squares for the y data. So these graphs show us correlation between the weight and chest of birds. So you can see that on my top right, that is the top graph shows a positive, strong correlation. The values are running from the left to the right to the left top. Then all this is weak correlation. As you can see, it's almost zero. And then you have moderate or almost strong correlation. So if the values are running from the bottom, the top right to the bottom left, that is negative correlation. You can see it is strong correlation. And here it is weak correlation. It's almost close to a random scatter of points. Then we have minus 0.62 correlation. You can see it is so different from 0.93. Now, correlation is not causation. Just because two variables are correlated doesn't mean one causes the other to change. For example, if we look at religion and crime, we will not say that being Catholic causes people to make a sign of cross, or being Catholic makes somebody to go to church every Sunday, or makes somebody to commit murder in every month. So if there is a correlation between religion and crime, it may not necessarily mean that religion causes crime. So there might be other factors actually causing crime. There is one of our hospitals is surrounded by very many trees, and there are very many marb stock birds on the trees, but they also produce a lot throughout the year. But we also find that the women in the hospital, in that particular hospital, are also producing throughout the year. It does not necessarily mean that when the women are producing, even the birds are producing. So one causes the other to change. It doesn't make sense, is it? The birds cannot cause the women to give birth. Neither can the women cause the birds to give birth. So correlation is just showing us that there is a linear association, which can either be positive or negative, but not a causal relationship. If we want to find out a causal relationship, we have to perform an experiment. Then we'll be able to know whether the birds cause the women to give birth, which is not true anyway. Correlation coefficient denoted as R. In R, we can compute correlation coefficient using those functions you see. Then we can run them in R. For example, if we want to get both the correlation and the p-value, then we run co.test. In bracket, we have to put the variables, as we shall see in the practicals. So as I say, there are various types of correlation. We have Pearson for continuous data, Kendall, Spearman for categorical data. Kendall is specifically for data which is in form of ranks. Okay. So we have a graph here. It's a scatter graph. So we can see that R can allow us to construct a scatter diagram, which can be used to tell us whether we have a positive linear association or negative. So in this graph, we see that price and weight of diamond are related, and it is a positive linear association. So when we go to practicals, you'll be able to construct the scatter diagram using the Gigi scatter command. So we can compute correlation, as I said, using the function call .test, and inside the brackets we put in our variables. For example, here we have diamond and $ weight, meaning go in diamond dataset and select weight. Then we want also the correlation for price. So in the same dataset diamond, go and select price. And method, we are going to use Pearson because the dataset, the variables are continuous. So below there we get an output. And the output shows us that diamond has weight and price. The two are correlated, and the correlation value is 0.924. It shows a t value and a p value, which is 0.00 something, meaning that there is significant positive, strong correlation between weight and price. So where do I get strong? The correlation value, you can see it is down here. It is 0.9246. It's almost close to 1. And the p-value is less than 0.05, indicating that weight and price are significantly, positively, strongly correlated. So the two variables are strongly correlated. So this is the same interpretation. You can see that it has been magnified. We get a t-value for the test, the degrees of freedom. The p-value is less than 0.05. We can also get the confidence interval within which the correlation value of 0.9 lies. So this confidence interval, we know that statistically we say that if you repeat this experiment 100 times, then you compute 100 confidence intervals. 95% of the time, they are going to include the value of the correlation, which is 0.92. On the other hand, you are 95% confident that the value of correlation, which is 0.92, is included within the confidence interval of 0.88 to 0.949. And because the p-value we've computed is less than 0.05, then the correlation is significant. Okay. So in R, we can use the correlation matrix to investigate the correlation between many variables. So if you have like 6 variables, then you use the correlation matrix. We also need the package called HMISC to compute the R correlation for the correlation matrix, and also to run regression, as we shall see. So after doing correlation, correlation is the descriptive analysis of regression. So before we conduct a regression analysis, we have to find out whether the variables are correlated, whether the response and the independent variable are correlated. We also want to find out whether the association is linear or not linear before we go into linear regression. So if a pair of variables has significant correlation, then the relationship between the data values can roughly approximate a linear equation. So the process of finding the linear equation and also getting a line of best fit is called linear regression. And the line of best fit is called linear regression line. So before I continue in the chart, can I continue, or there's somebody with a problem? Why do we need a p-value for correlation? To find out whether it is significant. Significantly different from 0. Okay, so I'm going to continue. Yes, today's session is being recorded. If you see on top here, there is an icon which shows live, meaning it's being recorded. Helen is telling me that she has shared the link for today, but she will share it again so that... okay, so let's go to regression. Oh, regression does what correlation cannot do. Actually, if you do regression, you can get correlation. Here are the objectives of regression. Regression is concerned with a study of relationship between two variables, with an objective of identifying the relationship, whether it's linear or nonlinear or curvilinear, estimating the parameters of the relationship By parameters, we are looking at the intercept and the slope and validating the relationship. By validating, we mean we are going to look at the assumptions under linear regression and see whether they are not being violated. So if the assumptions are violated, then the relationship is not right. Okay? So that's what regression does. It does more than correlation. Remember, correlation is just showing us whether there is a linear relationship and the direction of the relationship. So in a linear relationship, we have this relationship where y is our response, b naught is the intercept, and b1 is the slope, x is the independent variable. b1 is the slope of the line, sorry about the typo, and it indicates that for each unit increment in x, then y increases by the amount of the slope, while b0 is the intercept, which is the value of y when x is equal to 0. So the slope b1 describes the change in y for every unit change in x, and b0, that is the value of y when x is equal to 0. So we can use the line of best fit to do prediction. That is the other objective of regression. So once we obtain the intercept and slope, then we can predict the value of y at any given value of x. But we also find that the line of best fit does not touch all the values in our scatter diagram, as we shall see. Now, the difference between the observed values, the y values, and the predicted values is what we call our residue or error in the predicted line. How do we determine the intercept and the slope? We use what we call least squares, least ordinary squares, LOS. Now, the least squares try to minimize the difference between the observed value and the fitted line. Okay? And when we use the method of least squares, then the parameter, the intercept and slope, are called least squares estimates. So here is a line, is a scatter diagram. The blue line is the fitted line, which has been fitted using ordinary least squares regression. And the regression line, after fitting the blue line onto the red observed values, is y hat, because it's an estimate, is equal to the slope beta 1, x is the independent variable, and beta naught is the intercept. So you can see that the blue line does not pass through all the points. So the difference between the red points and the blue line is what we call our residue or error. So let's go and see a graph. So this particular slide is telling us that the observed minus the predicted values gives us the residue. So how do we get the predicted value? We talked about the line of best fit, which has this equation here. So for any value of x, we can predict a value of y. And if we plot those values, then they lie on this line here. And the difference between this blue line and the red gives us our residue. So here is a plot showing a scatter diagram and also showing you the predicted y hat and the observed value and the residue. So you can see that the red points are the observed response from the field, and when you fit the line, the model line from regression, we will see that it doesn't touch all points, and the difference between the blue line and the observed value gives us the residue. Okay? So ordinary least squares regression minimizes the sum of square difference between the observed and the predicted value. So let me go back a little bit to this equation here. When we sum the difference between this line and observed value, then differentiate with respect to slope and intercept, we are able to get the equations for calculating the slope and intercept of the line. So once least squares fits a line, or best fit the blue line, then we are able to get the difference between the observed and the fitted values, differentiate, square the difference between observed and fitted value, differentiate with respect to beta 1 and beta naught, and then we are able to come up with the equations that most people don't want to look at. So the equations that we obtain using the ordinary squares for the estimate as beta naught and beta 1, remember when we present the equation with small b naught, that is a statistic, and beta now is a parameter. When we are testing hypothesis, we test the parameters. We don't test the small letters, which are Roman letters that signify the statistic. Okay, so that is the difference. So beta naught is the intercept, and it is estimated with this equation here, which is the mean of y minus the slope into the mean of x. Now, the slope is the sum of the square of product of x and y over the sums of squares for xx. So the expansion of these formulas are below here. If you're interested in doing the real math of this regression, this is just a by the way. Don't worry about the math. So on the other hand, you can present them in an expanded form. Okay? So we are going just to flip through these equations. I just wanted you to know that these equations come from these formulas. And when you go back, when you're taking a cup of tea this evening, you can get a short data set and compute those intercept and slope. Now, the residuals we've been talking about are the deviations between the observed and the predicted value. They are denoted with the letter E, which is epsilon. You can see the formula: y is the observed minus y hat the predicted. So on the plot, the difference between now the red line and the thick red points are our residuals. So for each response you collect from the field, you can calculate the residue. Okay? The residuals are useful in computing the error sums of squares, which we call experimental error in experimental design, when we talked about the analysis of variance under experimental design. So the experimental error in under experimental design is the same as the error sums of squares under regression. So we use the error sums of squares to find out whether there is a significant linear association between the response and the predicted value. So as we shall see, okay? So the estimate of the mean square error under regression is the sums of square error over the degrees of freedom, which is n minus 2, where 2 is the number of parameters in the regression equation. We only have 2 parameters, the slope and intercept. Okay? Okay, so then SST is the total variation in the response, which is the sum of the square difference between the observed minus the mean of the response, gives us the total variation. And that total variation is divided into the regression, sums of squares, and the residual or error sums of squares. We also have what we call the coefficient of determination, which is R squared. When you're doing model building, R squared is important, and also when you do multiple regression. and also when we are looking at whether the regression model fits our data. R squared tells us the amount of variation explained in the response after fitting the model, the regression model. Okay? So when you compute R squared, we look at the regression sums of squares over the total sums of squares, gives us R squared, which tells us out of 100% variation in Y, when you fit X, the independent variable, then it is going to explain either 60 or 70, depending on the data set. Okay? So we shall see as we go on. So we've just talked about the coefficient of determination, R squared. Now, when you get the square root of R squared, you get correlation. You remember you asked me, is correlation better than regression? When we get R squared under regression, the square root of R squared gives us correlation coefficient. Okay? We've said R squared is the proportion of total variability explained in the response by the regression model. And it is obtained by dividing the regression sums of squares over the total variation of the model. We have R squared, then there's also adjusted R squared. R squared is suitable for a simple linear model. What is a simple linear model? This is a model where we have only two variables, one response and one independent variable. Now, if we have a response and many independent variables, that regression becomes multiple regression. And R squared is not suitable when we are looking at multiple regression. Why? Because it is affected by the number of independent variables added in the model. As you add more independent variables in the model, R squared changes, it increases. And we don't want it just to increase for the sake. So R squared adjusts for every parameter you add in the model. So if we have a simple model, which has only the intercept and slope, if we add another variable, we are going to have one intercept and two slopes. It means that when you add an extra slope, R squared is going to adjust the R squared by the added parameter. But R squared is just going to increase. So we want to compare our models well, so we use the R squared adjust when you're doing model building. Helen is going to talk about model building. So how do we know that we have a significant linear relationship? We have hypotheses that we state under linear regression. And the null hypothesis under linear regression, we are testing the slope, whether the slope is different from 0. And if it's equal to 0, then there's no linear relationship. We have just a straight line model. And if the slope is not equal to 0, then there is a linear relationship between the response and the independent variable. How do we test this hypothesis? We use a t-test under regression. There are also other types of t-test. There's a two-sample t-test, a pair t-test. Those ones when we have one variable or two variables, depending on what you're investigating. But this is under regression. And that t-test is between the slope of the model line over the standard error of the slope, whose corresponding degrees of freedom is n minus 2, and 2 is the number of parameters. Okay. So before I go to the assumptions of regression, in the chart, should I continue or there is a problem? Okay. Okay, thank you. I have some few questions here. What is the difference between regression and ANOVA? It's actually, the question should be, what is the difference between regression and experimental design? Because under regression, we have actually ANOVA. We said ANOVA was a statistical technique that separates the total variation in the response into, under experimental design, it's called treatment variation. Under regression, it's called regression, sums of squares, and the residue or experimental error. So the difference is that regression, we are looking at two variables which are continuous if it is linear, simple linear regression. ANOVA, we are looking at the response which is continuous and the independent variable which is categorical. Just like we looked at the treatments and the response, yield or growth. Here regression, we are looking at growth and probably the weight. We are looking at yield and we are looking at amount of fertilizer. How do you, okay, that question is not clear. What's the difference between regression and correlation? Okay, correlation, as I said, is the descriptive analysis under regression. When you want to find out whether two variables are linearly related, we first of all find out the correlation value, which tells us that there is either negative or positive relationship between the two variables. Then if we find that the correlation is significant, then we go ahead to use regression to confirm whether the relationship is linear or nonlinear, curvilinear, etc. Should one conclude that a higher R squared in regression means the wrong model? No, I've said that R squared for simple linear regression, it's okay. But as you add in more variables in the model, it increases, it is inflated by correlation between the independent variables. So what happens is that you're better off using the adjusted R squared because it is adjusting for any parameter added in the model. Why degrees of freedom now n-2 instead of n-1? n-2 corresponds to the degrees of residue or error degrees of freedom, which is n-p. And for simple linear regression, the number of parameters are 2, the intercept and slope. That's why we have n-2. And n-1 corresponds to the total variation degrees of freedom. Okay. I think those are the questions. So let's continue to the assumptions of linear regression. So we said when we were introducing statistical models, we said that they have assumptions. And those assumptions have to be valid for that statistical model to be valid. Okay? So if they are violated, then we have to find a way to make sure that those assumptions are valid. As we saw, we can use transformations, we can use models which suit the response. For example, I gave an example. If you have a binary response, then you don't need to use a simple linear regression. We can go in for logistic regression to model the distribution of the response. Okay, so the assumptions under linear regression, we assume that the response is a random variable, which is normally distributed with mean mu and variance sigma squared. We also assume that the random errors, the unexplained variation, residue, those are the names for random errors, are assumed to be independent, normally distributed with mean 0 and constant variance sigma squared. So those are the assumptions. They are elaborated more. We will elaborate more about the assumptions as we go on. So an isovariance table under regression. It consists of the total sums of squares, the regression sums of squares, and the residue. Okay? So here are the simple formulas. We will not go through them, but let's go to this already analyzed data set of regression. So the relationship is between volume and diameter. Volume being the response and diameter being the independent variable. So what I want us to look at is the degrees of freedom. regression degrees of freedom is equal to the number of parameters in the regression model minus 1. That's how we compute the degrees of freedom for regression. And in the model, if you look at our model, volume is equal to the intercept and the slope. So there are two parameters, minus 1, we get 1 degree of freedom. Now, residual is equal to n minus p, the total number of observations minus the number of parameters. In this model, we have only intercept and slope, 2 parameters. If we look at the total degrees of freedom, they are 30, meaning that the total number of observation is n minus 1 is the degrees of freedom. So n, if we get the degrees of freedom plus 1, gives us the total observations. And for residual, it is n minus 2. So if we get 31 minus 2 gives us 29. I hope that is clear. Is that clear? The degrees of freedom. Let me see in the chart. Okay. Okay. Is it clear? Should we continue? Somebody is saying no. When you say no, make sure you indicate your problem. Julia, what is the problem? You can indicate it in the Q&A. We can pick it later. Okay. Understanding something after so many years. Interesting. Okay. Okay, thank you. Okay, so let me talk about the total degrees of freedom. We know that the formula for getting total degrees of freedom is n minus 1, which is equal to 30. So if we want to get n, we are going to cross the minus 1 over the equal sign to go on the other side, the positive side. So the minus 1 becomes positive. So 30 plus 1 gives us 31. That's why when it comes to the residual here, I'm saying 31 minus 2, giving us 29. Sums of square, you saw that the formulas. Mean square is the ratio between sums of square and degrees of freedom. You can see that when we divide 7,581.8 by 1, we get the same value here, the mean square. Also here, mean square error is the sums of squares error divided by the degrees of freedom. The F ratio is the mean square regression divided by the mean square error. That is the F ratio. And then we can compute the corresponding p-value. If you've done probability, you should be able to compute the corresponding p-value. But we are not going to compute anything now. Let's learn how to interpret these values. So we are stating our hypothesis that there is no linear relationship between volume and diameter. That's our null. And the alternative is that there is a linear association between volume and diameter. Now, we are going to use a significance level of 5%. And that is the probability which we assume that the null is correct. So if we get a value smaller than 0.05, then our chance for the null to be correct has reduced, and we have evidence to reject the null and conclude that there is a significant linear relationship between volume and diameter. The p-value I'm using is 0.000. Okay? Okay. Now, we see there is a value S here. S is the square root of mean square error. Mean square error is the variance of the data set. So if you get the square root of 18.1, you'll get 4.2. So that is the S. This is our R squared, which is 93.5%. So our R squared here shows that the amount of variability explained in volume is 93.5% by the regression model with diameter. So after fitting diameter, 93.5% of variation in volume has been explained by the regression model. Now you can see R squared adjusts is not equivalent to R squared because it adjusts for any parameter. When you put the intercept plus the slope, it keeps on adjusting. Okay? Okay. So let's go to the next. Okay, so this is just interpreting what I've just been saying, and we can actually use also the F value for interpretation. But since we are going to do practicals and get these values practically, we can use the P value. But here I've indicated the value which is in the F distribution table. So if you go to the F distribution table at 5% with denominator degree of freedom 1 and numerator degree of 29, the corresponding value will be 4.18. How do we use it to compare with 419? If the calculated value is greater than the tabulated value, as we can see here, then we have evidence to reject the null. That is if you're using the F value. So if this F value we've computed, 419.36, is greater than the tabulated value at 5% significance level, so we have evidence to reject the null and conclude that there is a significant linear relationship between diameter and volume. Okay, so that is interpretation. So there is an exercise for you at the end of the day. You will go to the notes and pick this data set, and please answer these questions under simple linear regression. We have a simple exercise which I want you to attend to after we've done the practicals. So you will use it with R. So tomorrow morning, please, I would like to see somebody presenting something. So try to attempt this using R. The data set is right there. So that is for simple linear regression. So let's talk about the residuals. We say the residuals were important. Important in estimating the mean square error, which we use to test whether there is a linear relationship between the response and the independent variable. And we get these residuals by subtracting observed minus fitted values from the model. And we also know that for our inferences to be correct about our model, the assumptions which I mentioned should be valid. So how do we check that those assumptions are not valid? We use the residual plots. Just like we saw under an experimental design, we also tested the assumptions. So even here, we test the assumption. So if the model is correct, the residuals are assumed to be normally distributed with mean 0 and constant variance sigma squared. The residuals are assumed to have constant variance and no correlation, meaning that the residuals are independent of each other. So how do we test those assumptions? A histogram of residuals is used to check for normality. So if we see a histogram that has a bell-shaped curve, then we know that our residuals are normally distributed. Or we can use a normal probability plot, which is a plot of residuals versus normal score. And if the observed values lie on the line, normally it is either red or blue, then the data is normally distributed. We shall see that in the practicals. To check for constant variance, we use a plot of residuals versus predicted values. So if we observe a random scatter of points, just like you see in this plot, then we have constant variance. Anything that deviates from what you see, like I explained the other time, if the residuals are increasing with increasing fitted values, if we see a funnel-shaped curve in our plot, then the residuals are increasing with the fitted values, indicating the residuals are heterogeneous. They do not have constant variance. Okay? Now, for independence, we construct a graph of residuals versus order of values. Then it gives us a pattern. If there is no time series pattern, then the residuals are independent. If you observe a time series pattern, then the residuals are not independent, and we need to include time in our model, either run repeated measures analysis or run time series analysis. Okay, so these extra slides are just an expansion of what I've been talking about. So I am going to go to multiple regression. In the chat, should I continue? Okay. You're welcome. Amen. Amen is going to come to Makerere. Okay, thank you. Okay. So we are going now to look at the theory of multiple regression. After this, then we'll switch to R. Let me check the time. Okay, we still have 1 hour to go. So hopefully in 20 minutes we'll be done with multiple regression or less. And then we go to R and do these things practically. Okay, so somebody asked a question, what is repeated measures and time series? Time series is when you consider time as part of your analysis. You know, like your data varies over time. And also repeated measurement, you have an experiment performed, but you're measuring yield over time. You're measuring yield every week or every month. So we find that the data you collect on month 0 is correlated to month 1, is correlated to month 2. And with our normal ANOVA, we cannot account for the correlation over time. So we use repeated measures analysis. Normally, what is most suitable is what we call mixed model, which my colleague Thomas is going to talk about. So we will briefly introduce repeated measurement. I think after tomorrow, we will introduce repeated measurement. Then my colleague will also talk about mixed model, how it helps us solve the problem of correlation between data. So normally people collect data over time on the same experimental unit, but they ignore and either analyze it as MANOVA or using ANOVA, which and assumptions under those two break down, as we shall see. Okay. So multiple regression. Now, sometimes you find that the response does not only depend on one factor. And in your data set, you have so many independent variables. So you will find that maybe you fitted volume versus diameter, but it is only explaining 50%. So that means that there are other factors you need to include in the model to explain more variability in the response. And when you have one response and many independent variables, that type of regression is called multiple regression. When you have more than one predictor variable related to one response, that type of regression is called multiple regression. How about if you have many response and many independent variable? That type of regression is called multivariate regression. Mult means many, regression. Okay, so there are two types. Multiple regression, one response, many predictor or many independent variables, and many response plus many independent variables. We run what we call multivariate regression. So we are going to look at multiple regression now. So a model under multiple regression can either consist of an intercept and many slopes. So you can see we have B0 is our intercept, and each independent variable has a slope. X1 has slope B1, X2 has slope B2, and whatever remains which is unexplained is called epsilon, which is the random error due to other factors not included in the model. Now, the assumptions under linear relationship, which we've just talked about, where we assume the response is normally distributed. We assume the errors are normally distributed. We assume the errors have constant variance. We assume the errors are independent. Also hold for multiple regression, and we add on one extra assumption that the independent variables are not correlated. So in addition to all the other assumptions under simple linear regression, they hold for multiple regression, and we add on one extra assumption which indicates or which states that the independent variables should not be correlated. Okay, so we can find out whether the independent variables are correlated using correlation analysis, or we can even construct a scatter diagram. Okay. So if we conduct a multiple regression and get an output, this is an output from multiple regression, and our regression equation has volume is equal to minus 58.0 plus a slope value for diameter and a slope value for height. So how do we interpret this regression equation? For us to be able to interpret the slope and intercept under multiple regression, we are going to hold height constant. So we assume height is not there. So we hold it constant and then interpret diameter. Then afterwards we hold diameter constant and interpret height. So let's start with diameter. We hold height constant. So in this equation that you see, for every unit increment in diameter, volume increases by 4.71 the units of volume, either cubic meters or cubic centimeters. So for every unit increment in diameter, volume increases by 4.71 cubic units. And the intercept is the value of volume when there is no diameter or height. Now, if we hold diameter constant and interpret height, for every unit increment in height, volume increases by 0.339 units cubed. I repeat, we hold diameter constant and interpret the slope for height as for every unit increment in height, volume increases by 0.339 units cubed. Now, what if we had negative values for slopes? Assuming that the sign in front of 4.7 is minus, then we are going to say that for every unit increment in diameter, volume decreases by 4.71, assuming that there is a minus here. Okay? So if it is positive, the response is increasing. If it's negative, the response is decreasing. Sometimes the intercept doesn't have a meaning. For example, in this case, we have a minus 5.8. So what do we say? That the trees are not there or the trees are still young? That one is your assignment to find out. Okay? So let's look at the output down here. When you analyze your data, you get coefficients. So you can see that these coefficients here are the ones I've used to write my model. The intercept, the slope, and the slope for height. They have corresponding standard deviation and t-value and p-value. So for diameter, the p-value corresponding to diameter is just showing us that there is a significant linear relationship between diameter and volume. And then also the p-value of 0.014 corresponding to height shows that there is a significant linear relationship between volume and height. R-squared adjust. We are going to look at R-squared adjust. It is now the one that you use for interpreting the amount of variability explained in volume by the model, because R-squared increases with every parameter you add, with every independent variable you add in the model. So in this case, the amount of variability explained in volume by regressing volume onto diameter and height is 94.5 4%. Okay. So we shall see this very visibly when we are doing model building. It's very interesting when you're doing model building and you see how R squared is inflated by correlation between the independent variables. Okay. Okay. So this is the analysis of variance table. You remember that in under experimental design, we also have an analysis of variance table. Even here, we have an analysis of variance table. The only difference is that both of these values are continuous. The variables are continuous, while in the experimental setting, the independent variable is categorical. Okay. So pardon? The constant. Okay, let me go back. The constant corresponds to the intercept, okay, which we said is the value of volume when we have no diameter or height. But if you put it biologically, if we don't have diameter or height, then maybe that is a seedling we are dealing with, because these are trees we are looking at. So in that case, I was saying that sometimes the intercept doesn't have a meaning. Sometimes it has a meaning. When you're dealing with some mathematical formulas, the intercept has a meaning. If it's negative, it has a meaning. In this case, I think the intercept doesn't have a meaning. Okay, so because it's negative and we are dealing with volume and diameter and height. So if diameter is 0 and height is 0, the volume is minus. We need to investigate that one. Okay? And I said it is your assignment this time to investigate. So this is the ANOVA table, which you get under multiple regression. It's just similar to simple linear regression. And you can see the regression degrees of freedom are now 2, because in our model here we have 3 parameters. So 3 minus 1, we have an intercept, a slope for diameter, a slope for height. Minus 1, we get 2 degrees of freedom. The total values are 31, minus 3, we get 28. So the p-value is just testing that overall there is a significant linear relationship between volume and height and diameter. Down here we get what we call sequential sums of squares. These ones I used another package called Minitab. It gives sequential sums of squares. Sequential sums of squares, when you add these up, you get the regression sums of squares. So it tells you of this total 7,684.2, how much is contributed by diameter, how much is contributed by height. We can see that diameter is contributing most to the variation in the regression. So that means diameter is more important than height in explaining the variability in volume. But remember that these are numbers. You have to go and read your biology behind trees and find out, if I remove height in the model, can I estimate volume? So these are numbers. So when you're interpreting the numbers, don't forget your biology. Go and read about the system and associate it with the numbers. So if we were doing model building, we would say height does not explain a lot of variability in volume. But at the same time, when we are computing volume, we need a height. There's no formula where we don't have height when we are computing volume. So we leave height in the model for that purpose. Okay. So another example, which I'm going to use in the R, is this. We are investigating the relationship between water uptake, food intake, and egg production. So there are 12 birds which were investigated, and want to find out if we want to go and do this business of bird rearing, how much food do we need, how much water, and how much eggs are we going to produce at the end of the experiment. So that's what we are going to do. So that's the data. And okay, there's something about indicator variables. Now, sometimes your independent variable is categorical. For example, variety, species, fish type, water quality. So if you have a categorical independent variable, we formulate what we call dummy variables. Okay? We formulate what we call dummy variables for that qualitative variable. And for assuming we have type of fish, and the fish are two types, so the number of dummy variables is going to be equal to the number of categories, which are 2 minus 1, meaning you only need one dummy variable. So how do we formulate the dummy variable? I'm going to stop sharing and share our document where we can write. So let me first of all exit. Okay. So this is a blank script. I hope you can see the Word document which I have shared. Is it visible? Have I talked? Okay. Okay, so we are talking about dummy variables. We say that if you have a qualitative, okay, so we have our qualitative variable called a fish species, meaning the type of fish, and we have tilapia and Nile perch. I'll talk about what I know. I don't talk about Solomon. Okay, so we have these two types of fish and they are very tasty. If you come to Uganda and you visit me, I'll cook for you Nile perch and tilapia in banana leaves. Okay. Okay, so we have these two types of fish as part of our independent variable. We are modeling weight of fish, and maybe we could also have amount of food that the fish was eating. So we were raising tilapia and Nile perch, and we are giving them a certain amount of food and weighing their weights. So weight, gain in weight is the response. And we want to run a regression analysis between weight and species. Okay, so we are going to create a dummy variable because the way they appear here, we cannot run our regression properly. So what we say that the dummy variable number of dummy variables equals to m minus 1, where m is equal to number of categories. Categories under the qualitative variable. Okay, so in this case, the number of dummy variables is going to be equal to 2 minus 1, which is equal to 1. So we are going only to create one dummy variable. So species, we have tilapia, and then we have Nile perch. I'll call it Nile P. Nile P. Then dummy variable here. So we are going to code our species, giving it numbers. They don't have any meaning, but for ease of computation. So we are going to say, if fish equal to tilapia, then the dummy variable is equal to 0. So we will award it. Where we see tilapia, we award 0. And where we see if fish is Nile perch, we award it 1. So that is how our data is going to appear, and then we have weight here. Okay, so we are going to have our weights, maybe 20 kilograms, and here the tilapia, they weigh more, maybe 40 kgs. Okay, so that's how our data is going to appear, and you're going to run a regression model between weight and the dummy variable. Okay, so that is what we call indicator. Some people call it indicator variable, others call it dummy variable. So that's how you formulate a dummy variable. Now, assuming we had a third type of fish, Solomon, although it is not here. So, assuming we had Solomon, that means the number of dummy variable is going to change to 2. So, I'm going to have dummy variable 1. Then I'll have dummy variable 2. I'll move my weights. So that is weight. Okay, now what if we have 3 categories? That means that we are going to have, I think this is a sparing. Okay, so we are going to create 2 dummy variables. And in this case, we will say if fish is equal to tilapia is 0, and if fish is Nile perch is 1, and if fish is Solomon is going to be also 0. Okay? Then dummy variable number 2. If fish is tilapia, still 0. We go to 2. If fish is Nile perch, 0. And if fish is Solomon, we give it 0. We give it 1. Okay? So, we've created 2 dummy variables. And the first dummy variable has 1 for Nile perch, the rest is 0. The second dummy variable, it says if fish is salmon is 1, the rest is 0. So that's how we create the dummy variables. And we can now conduct a regression between weight and the 2 dummy variables. If we find that the p-values corresponding to the dummy variables is significant, then we can now go in the nitty-gritty of writing the equations. Okay, so I hope this is clear about the dummy variables. I'm going to stop sharing and share the notes. Okay. Okay. So under dummy variables, we can have regression with the grouped data, and our grouped data is the data with categorical variables. And normally what we test is we have single line, meaning that you can fit only one line irrespective of the categorical variable. So if we find that the dummy variables are non-significant, that shows that we don't need any other model. We are going to fit only one model, will be suitable for both tilapia, for Nile perch, and Solomon. Now, parallel line means that we are going to fit 3 lines each line for a different species of fish, having different intercepts but similar slopes. Those are parallel lines. So that one shows that each fish type requires its own model. How do you know that? In the scatter diagram, when you construct a scatter diagram, you will see grouped information. The information will be grouped into 3. And that is the first indicator that you cannot fit only one line through all those groups. Then different line means that you have 3 different lines for the 3 fish species, meaning they have different intercepts and also different slopes. Okay, so that is about indicator variable. Okay, somebody says I should repeat even. Okay, single line means that you're going to fit one regression model and it explains the variability in species. We fit a single line if after fitting the dummy variables to the model, we find the corresponding p-values are greater than 0.05. So then we conclude that only one line is necessary for our data. Now, if the dummy variables end up to be significant, the dummy variables are going to stand for the different intercepts. Okay? In that case, we are going to have parallel lines, meaning 3 lines, different intercepts but similar slopes. Different lines means that you have different intercepts and different slopes. How do we get the slopes? We are going to get an interaction between, if our data set had weight of fish, species, and then amount of food, we are going to get an interaction between the dummy variable and amount of food and create a new variable which is going to represent our different slopes. Okay, so that is all about dummy variables. So any other type of regression is when we have curvilinear relationship, whereby the data set you have shows either a square or a cubic on the independent variable. That type of regression is called polynomial regression, whereby the independent variables have powers in the model. Okay. Lastly but not least, in case we find that the assumptions under our linear regression are violated, we can do transformations, and I've summarized them in our table. So if we find that we have data which is not normally distributed and the variance is not constant, then we can transform our variable. If it is a continuous variable, we can use the square root of the response or natural logarithm of the response or the reciprocal of the response to stabilize the variance and non-normality. If it's count data, we can use the square root of the response, we can use natural logarithm, or we can use square root of the response plus a constant. If the count is less than 0, we use the square root of the response, a square root of the response plus a constant, or natural log of the response plus a constant. If it's a proportion, we are going to use arc sine of the square root of the response. Okay. Apart from polynomial, linear regression, and in regression with groups, we have what we call nonlinear regression, where we model the distribution of data. And tomorrow, my colleague Helen is going to talk about logistic regression and log linear regression. In those types of regression, we model the distribution of data, and we call that nonlinear regression. Okay. Okay, if there is no question, we go to R, and let me check the time. We have 30 minutes. 30 minutes, I think we can do simple linear regression in R, and then we can continue tomorrow to finish. Okay, let me see in the chat. When you have a long comment, please put it in the Q&A, because now it disappears before I can read. Please clarify on creating dummy variables. Okay. The reference group is actually the one that you've named 0. That becomes your reference group. Please share the link for today. We've already shared. It is in folder day 7. If you let my colleague share the Google link, we've already sent you the link for today. Daniel says, let's go to R, and the rest can go to the YouTube for clarification. I'm sorry. Does transformation always turn the data to normal distribution? Yes, it does sometimes, but it is advised that, for example, if your response is binary, instead of going for transformation, you're better off doing a logistic regression to model the distribution of the data. Unless if you don't know the distribution of the data. Okay? But now, statistics has developed in that we can model the distribution of the data. So use transformation if it is last resort. If it is count data, we do log linear regression. Okay? Okay. Okay, let's go to R. I think I have clarified. The reference, when you set a categorical level to 0, that becomes your reference. Okay? That R does it automatically. Okay, let's go to R, please. Okay, somebody is saying I clarify on creating dummy variables. I'm going to stop sharing and share the Word document before we go to R. Okay. So, dummy variables. We say that if you have a qualitative variable, for example, fish species in your data set, you cannot just run a regression with the tilapia and Nile perch in your data. You may either run into problems, or when it comes to writing the model, you have a problem now to specify which one should I multiply with which one. When it comes to model building, things become difficult. So we code our qualitative variable for ease of numerical computation. So assuming we have fish species, we've performed an experiment. We wanted to know how much weight is gained by the different types of fish. And the first variable has tilapia and Nile perch. Now, we say that we can now code our tilapia as either 0 or 1. And we also say that the number of dummy variables we formulate if we have a qualitative variable depends on the levels of categories under the qualitative variable. Here, the levels of category under fish species are 2. So the number of dummy variables will be 2 minus 1, giving us 1 dummy variable. Okay, let me continue. So in the first example, we only have 1 dummy variable. Then I said, how about if the number of categories are 3? We even have salmon. Not in Lake Victoria, don't ask me. We only have Nile perch and tilapia. Okay, salmon is just hypothetical. It's not there in Lake Victoria. So assuming the fish species are 3, in that case, the number of dummy variables will be 3 minus 1, giving us 2 dummy variables. How do we formulate the dummy variables? We are going to say that the first dummy variable, we are going to say that if fish is Nile perch, we are going to code that fish 1. The rest of the category, we call them 0. So the first dummy variable is defining the fish Nile perch. So in our data, for tilapia, we put 0, Nile perch 1, and salmon 0. Now, for dummy variable number 2, if fish is salmon, we will call it 1. The rest will be called 0. So tilapia will be 0, Nile perch 0, and salmon 1. Then we said we include our weight, which we are investigating, and probably we even have another variable amount of food given to the fish, which we are also using to see whether the fish are going to gain weight. Okay, so that is how we create dummy variables. And then after creating dummy variables, you're going to go into your R and regress weight onto dummy variable 1, dummy variable 2, and also amount of food. Then look at the p-values. If they are significant, then that is another story. We have now to look at how the dummy variables can help us to formulate new or different models for each fish type. So I say that if we run the regression between weight and the 2 dummy variables and food, and we find that the dummy variables are non-significant, but food is significant, that means that we actually need only a model with weight and food to model weight gain in tilapia, Nile perch, and salmon. We don't need to have different models for the different fish species. If we find that the dummy variables are significant, as you see them, what happens is that these dummy variables are going to help us specify the value of the intercept for both tilapia, Nile perch, and salmon. Let me give an example. Assuming this is our model. So then we are going to put here 60. And this is our model. Weight gain is equal to the intercept may be 30.1. This is hypothetical. I'm just giving for the purposes of understanding. Is equal to the intercept for food uptake may be 20.1. Oh, sorry about that. Plus, this is food, then minus dummy 1. So the dummy 1 is going to have an intercept maybe 2.2, dummy 1, and then plus 0.3, dummy 2. Then, so that is our equation we've gotten from the regression analysis. So what we are going to do, we are going to say, let me use the same, lower this down so that it's visible. So this is the overall model. We've seen that dummy 1 and dummy 2 are significant. So the equation for tilapia. We said the code for tilapia is 0. Wherever we see dummy variable, we put a 0. So in that equation, weight for tilapia is going to be modeled like this. It's going to be equal to 30.1 plus 20.1 food, now minus 3.2 times 1, because we say times 0, okay? Then plus 0.3 times 0 also. Because we said for dummy variable 1, tilapia is 0. For dummy variable 2, tilapia is 0. So our final model for tilapia is going to be weight is equal to 30.1 plus 20.1 food. So that is our model for tilapia. Let's do only one. Let's do Nile perch. Equation for Nile perch. For Nile perch. Nile P. We said Nile P for dummy variable 1 is 1, isn't it? Equal to 1. Okay. So in the equation, it's going to be weight is equal to 30.1 plus 20.1 food minus the first dummy variable we said it is equal to 1. So we are going to multiply by 1. Now plus 0.3 times 0, because the second dummy variable, tilapia, is 0. So the final model is going to be weight is equal to 30.1 minus 3.4. We are collecting like terms, 3.2. We are collecting like terms together. Yes, plus 20.1 food. So 30.1 minus 3.2, what is the value? Can I see in the chart if people are not sleeping? Okay, 26.9. Okay, so the new equation is going to be weight is equal to 26.9 plus 20.2. Okay, so you can see that the equation for, I'm going to make it maybe which color? Brown. The equation for tilapia has the same slope as the equation for Nile perch, which I'm going to put in green and make sure. So here, this is food. Okay? So if you want to know the weight for Nile perch, this is the equation you're going to. So if you're given a certain amount of food to feed a certain Nile perch, then its weight is going to be modeled by this equation in red. For tilapia, you're going to model it with this equation in green. Okay? So that is now when you have a categorical variable. So you can also find an equation for salmon. So that is the most important thing. When you have categorical variables, you can also run a regression. That's why I brought it up. Okay, I hope that is clear. And let's see how many minutes we are left with. We have 17. Okay, we shall do something in the 17 minutes. Okay. Somebody is asking, where is 20.2 coming from? That must be a typo. Sorry. Sorry about that. Let me correct it. I can see you're real attentive, and that is great. Okay, so that's a typo. Thank you. So let's turn to R and do something in R, and then we'll finish tomorrow. Okay, so thank you so much. So let's Stop sharing. I'm going to share R. And our script is called co and reg. So correlation and regression. So I hope everybody now is in R. Let me see in the chat. Are we all in R? Which script? The script is called co. Let me type it here. So the script is called co. Okay, that is the script. Please louder. Oh dear. I have typed the name of the script. You want a registration link? Helen, please send the registration link. So let's go into R, please, for the remaining minutes and utilize those minutes. Thank you, Helen. The registration. Okay, so in R, the first thing we do is to set our directorate so that we don't get lost. Our data set, where you stored your data set, and the data set we are going to use is called egg production. It's called egg P. Where you stored egg P is what we are going to set the directorate to. So I'll just go to view, no, session window, sorry about that, session window, set working directorate, choose the working directorate, and practice, that is where my working is. So you all set your working directorate. And next we load our packages. We load our packages. Let's load until Gmodels. In case you don't have OLSRR, load until Gmodels, because I don't know whether you have all these packages. And in case you don't have those packages like HMISC, install the package, please. If you do not have Gmodels, install the package. If you don't have ggplot, install the package, because we need these packages. So we are going to load them, and I can load ORS because I already have it on my computer. But in case you don't have OLSSR, please install that package. It is called OLSRR. You use the command install.packages in inverted commas OLSRR. Okay? Then when you run that line, you'll be able to load it. So I'm giving you 2 minutes to finish loading the packages. Okay, so after running, I am assuming, let me see in the chat, are we at the same page? You're able, or if you can't copy the link, please just click in the link. Otherwise, you can actually copy that link, put it in a Word document, and then run. You can double click on it and get the folders. I see somebody has an error in installing OLS. Hopefully the spelling was right. Put your comment in Q&A, because now I can't see the Q. Yes, we've sent the materials for today. It is in day 7. Day 7. And if you don't have the link, you can scroll up. Get the link. I see the link here. Let me just copy it. I'm pasting the link. There you are. So you can just go and actually click on the link in the chat and it's going to open up. Or you copy, put it in a Word document. Okay. I have also sent the link for the registration today. If you've not gotten R running, I think what you do is just listen and follow. Then later in the day, you can download the YouTube videos and follow slowly when you get the R running on your laptop. Okay, so I can see that everybody is okay. I'm going to continue. We've already set the directorate. We are going to import our data. It's called egg, and we are going to use this command, read.csv. If you run that command on line 33, and then run the command on line 34, you're able to get the data set. So I can see the data set has water uptake, food uptake, and egg production. Okay. So I'm assuming that everybody has gotten that data. Am I right? Can you say yes or no? Have you been able to import? Enlarge your script. Okay, I'll do that in a minute. Okay, thank you. Let me zoom in. Okay, so that is how far I can go, enlarging the script. So you can see you have water uptake, egg, food uptake, and egg production. Okay, next we want to view our data. We want to visualize our data using a scatter diagram. As we said, a scatter diagram is descriptive statistics for regression. It's the one which tells us whether the two variables are linear related. So we are going to use the plot function, and the data set is egg. In egg, we are looking for food uptake, and we're also looking for water uptake. So let's run line 43, and it gives us, we get a scatter diagram. I'm going to zoom the scatter diagram and share it. So this is what I have. I hope that's what you have in your screen. What can we see in the diagram? Because now we are doing descriptive. What are you going to write? Assuming this is your project, what will you write on figure 1? Figure 1 is a relationship between water uptake and food uptake, or food uptake. What do we write? Let me see in the chart. There is a linear relationship, strong positive. Yes, continue. Let me see more. What do you see in the chart? Do you see any outliers? Strong positive. Okay. Okay. Great. Okay, thank you. So in the chart, we are seeing a positive, strong linear relationship between water uptake and food uptake. Okay. So let's go. I'm going to stop sharing and then share the script again. And in the script, I've put alternative way you can draw a scatter diagram. You can also use scatter.smooth. So let's just run line 47. And with scatter.smooth, it even puts a line for you. So I hope you can see that. I will not share it. Then you can also use a ggplot. So these are different ways you can, if we run line 50 of the same plot, we can see that a different scatter diagram is produced. A different scatter diagram is produced. Okay? So we have a different scatter diagram produced with a blue line. Okay? Then in the next part, you can actually split this line 50, you can split it into various commands, which you people can run in your free time. It's the same thing, you're going to get the same diagram, only that now we split it into sections. Like we give it an object and say ggplot, we specify the X variable and Y variable, just like Dr. Thomas was doing, creating an object that consists the plot. Then afterwards, you put a regression line. So I'm going to skip that, and I want us to go to customizing, to running a model. Is that what I want? Yes, I think so. Okay. So about the typo, please forgive me, I left some of the typos there instead of the title is price is a function of character. Current. So that is a typo, yeah. Okay. So let's go to line where we are going to compute the model. I want us to just look at the model. I have 4 minutes, I'm told. So let's run line 94. Tomorrow we can go backwards. Line 94, if we run it, we are going to get a model with intercept, and then the summary gives us the analysis of variance. So let's just look at that and call it a day. So I hope you can see that we have the first output just gives us the intercept and slope. And then the second part, which is summary in bracket the model, gives us the results. In the results, we have coefficients. And then we have the residual standard error on 10 degrees of freedom, the R squared, and the adjust R squared. Then we also have the F value and the P value. So if we go and look at the coefficients, so I'm going to select the coefficients. Here we are. If we look at the coefficients, we are interested in food uptake. The corresponding p-value is testing the hypothesis that there is no linear relationship between water uptake and food uptake, versus that there is a linear relationship between water uptake and food uptake. Now, once our p-value is smaller than 0.05, we have evidence to reject the null and conclude that there is a significant linear relationship between water uptake and food uptake. Then in the remaining minute, we can look at the R squared. I'm going to color it blue again. The R squared is 0.9562. It shows that 95.62% of the variation in water uptake has been explained by the model onto regression, onto food uptake, or 95.6% has been explained by regressing water uptake onto food uptake. Okay? So I think we'll end here. I don't want us to be stopped before we can even say A. So I want you to go and try out. There is an exercise in the notes. It's about simple linear regression. And I've just shown you how to do simple linear regression. Follow the R script and do simple linear regression. Okay, for that exercise that is in the notes. Tomorrow, let me have 2 people randomly presenting so that you give me more energy to go on. But if you don't present, I lose my energy. I only get energy from you guys. Okay, I am energized from what you tell me. So I would like to really thank you for paying attention, for being patient with us. We've been bombarding you with a lot of information, but you've persevered. Okay, so thank you so much. So tomorrow we'll continue with the practicals, and then we will have Helen coming in with model building. It's also an interesting part of regression. We cannot teach everything in regression, but hopefully with the time we'll be able. So thank you so much for being very good participants. So do my homework. Exercise 1 is part of the notes. Just import that data into Excel and then export it to R, analyze it, and then, yes, thank you very much. I am also flabbergasted by your patience. That's what the Americans say. Yeah. Okay. Okay. So have a nice day. Enjoy yourself. And yes, I will extend my thanks to Forum and Mercy and World Bank for making this possible. Plus Badea. Abadea has also done a great job. Okay. Okay. Yes, it is necessary to register each day. The funders are going to use those registration sheet to contact you. And also when we are giving you certificates, we are going to look at how often you've attended. Okay? So you better attend. And the more you attend, the more knowledge you gain. That means when it comes to, oh, the tilapia inside the banana leaf will come. I'm going to take a picture of it and post it online. But if you visit Uganda, you'll be able to taste tilapia in banana leaf. And we'll mix with the groundnut stew or peanuts, depending on where you studied from. Okay? See you tomorrow. When is the program ending? On Saturday. Okay, God bless you too. Please come and visit Uganda soon so that you can, even if you visited now, I would take you somewhere where they've prepared fish in groundnut stew. Okay, thank you so much. So, yes, I'll come to Namibia. If you invite me, yes, I will. Thank you. Okay, so I'm going to leave. I'm going to sign out and request the organizers also to sign out. Kwaheri, Kenya, and all the rest of the countries. Geostatistics, kwaheri, kwaheri. To Congo, to Zambia, to Nigeria, kwaheri, Botswana, kwaheri, Tanzania, mambo, Tanzania, Ethiopia, Somalia, wow, Benin, Gabon, Sudan, great, Burkina Faso, Kenya, wow, Hong Kong, great, wow. That has been really good. Kwaheri, all countries. Burundi, kwaheri. Zimbabwe, kwaheri. Yes. Uganda, kwaheri. Jia, kwaheri. Malawi. Ethiopia, Mombasa, Kenya, kwaheri. Cameroon, Guinea, Sudan. Wow, Ethiopia. I don't have words. Rwanda, kwaheri. Mama Africa, kwaheri. Okay, Mali, kwaheri. Benin, kwaheri. Zimbabwe,
India.
Nigeria, bye-bye. Kwaheri, kwaheri. See you tomorrow. Thanks for being great participants. Thank you. Thank you. You've done a great job. Kwaheri, India. Geospatial analysis using R. My dear, we shall talk about that privately. Kwaheri, kwaheri. Malawi, Cameroon. Okay. Please, let me, your phone number. Wow. Bye-bye. I'm leaving. Bye.
She's going to ask. Dr. Alice, when do you need this brochure? Okay, thank you very much. Praise. Thank you so much. What was those? Two more things.